One of the important elements of engineering practice is to be able to predict the behavior of the system that we design. For example, if we design a circuit, we should be able to predict how it will perform, how it will behave under certain circumstances. If we are designing a mechanical system, for example, then also we should be able to do that. And that is generally done by forming a mathematical model of the system, applying different types of inputs and seeing its performance. So, one elementary thing that most engineers should know is to be able to form mathematical models of systems. And these systems are normally very complicated in nature. The actual physical system, practical systems that you will have to deal with in your engineering life are normally very complicated in nature. But also the advantage is that in general they are composed of simpler elements. So, the simpler elements interconnected in specific ways ultimately form the whole system, and that is what we are trying to model. And what is the purpose of the modeling? Where the purpose of the modeling is to predict the dynamical behavior under certain circumstances. What do you mean by the dynamical behavior? If I give a certain input, what will be the output like, how it will, say if it is a mechanical system, how it will oscillate, how it will, different parts will move. These are the things that you are trying to predict. Now, these, as you know, are done with the help of differential equations that you have probably learnt in your first year mathematics, that all systems are changing in nature, moving in nature, dynamical in nature. So, whenever we are trying to find out how things change, that is represented by differential equations. Why? Because in a differential equations, in the left hand side you have got dx dt type term, where x is some variable. So, what does dx dt say? It says how x varies with time. And in the right hand side, in a differential equation, you will find certain function of the variable. So, if the variable has a particular value, say 1.2, you can find out what dx dt is. That means, you immediately know how it is changing at that instant of time, and then this way the whole thing unfolds. This means that for a more complicated system, we will have to write down differential equations. The one major element of this course of dynamics of physical systems would be to learn how to write down the set of differential equations for any given system, mechanical, electrical, electromechanical. So, however complicated it may be, you should acquire the ability of writing down the differential equations of the system. In the second part of the course, that means mainly after the mid semester examinations, we will learn how to understand the differential equations, how to handle them, how to solve them, but at the same time here the treatment will be slightly different from a standard differential equation treatment in mathematics classes, in the sense that our approach would be mostly geometrical. We try to understand the our focus will not be just to be able to algebraically solve a differential equation. Our focus will be to understand the dynamics of various types of systems. So, with that objective, we will learn how to solve differential equations and how to understand the dynamics. So, that is what the whole plan of the course is. Now, as I told you, a physical system that we often have to model, these are in most cases very complicated, but that complication is on the surface. In reality, they are not very complicated. Why? Because they are composed of elements. Now, here we will have to make one simplification. For example, suppose you have a spring something like this. Then if you want to understand the character of the spring, then as you compress it or elongate it, various parts will develop stresses, and how the stresses develop in individual points and how they move. If you try to consider that, that will become very complicated. Its spring itself will become very complicated. But then notice that ultimately whatever the spring is, whatever happens inside it, ultimately it interacts with the external world through the two extremities, right. So, other things are connected to the two extremities, and whatever happens inside, we will not concern ourselves with that nitty-gritty of whatever happens inside. We will talk in terms of whatever is seen at the two ends. This is called lumped modeling. That means, this whole thing is treated as a lump, as one single entity, which in a particular way interacts with the rest of the world. So, that will be one of the simplifications that we will adopt. And secondly, even though many of these individual elements like the spring can be very complicated, even the terminal characteristics can be very complicated, we will approximate by the simple characteristic, which you will for your information is not very far from the actual reality. So, how? First, let us come to the elements one by one. Even though you may understand the character of these elements, it will be illustrative to just pinpoint what we are interested in this course, and then go ahead. The first element that everybody knows is the mass. Mass is a technical term, but a general term is the inertial element, something that has inertia. So, the inertial element. Inertial element is anything, now we are generalizing it. You know that mass is an inertial element, but anything could be an inertial element. If the governing equation of that particular element is F is equal to dp dt, where P is the momentum. For the mass, you know, but you will see that later we will generalize this concept. So, this is the essential idea, that you apply a force on the mass, there is a mass, you apply a force, as a result of that the momentum changes, and the rate of change of momentum is exactly equal to the force. Okay. Now, the momentum, let us now consider the mass itself. Then the momentum is the mass times the velocity. So, it becomes m dv dt, or if the position of the mass is say measured from a particular point, position is q, then fine. So, if you write this, it is mass into acceleration, this part. That you would notice I have written very simply, but the force is a vector, momentum is a vector, v is a vector, q is a vector, acceleration is a vector, right. So, in general these are all vectors, and the moment you write it this way, the definition of mass, do you know what is the definition of mass? How do you define mass? I mean, for you it becomes an intuitive concept, but there has to be a definition of mass. The definition of mass is the proportionality constant between these two quantities. So, the moment you say between these two quantities, you see there are complications, because this is a vector, this is a vector, and you can have a proportionality constant between two scalars. So, what we actually do is to plot the magnitude of A, the magnitude sorry f, yeah, then you have a slope, and that slope is the mass. Clear? Then you cannot define mass, and for your information, there is nothing at rest. If something is at rest, you cannot define mass. Mass is defined by the property that it actively tries to resist any motion, any change in motion. That is how it is defined. So, only when there is change in motion, acceleration, change in velocity, you can define mass. So, that is the definition of the mass.
So, more generally, the mass could also be changing in the equation.
Mass could also be changing in the equation. That happens only in the context of the general relativity. Else, we do not consider mass as changing, unless you are putting in something with that mass. That is a different issue altogether. In case of a rocket. Oh, so, his question is that if the mass is changing in case of a rocket, then this slope will be changing all the time. That is it, nothing more. This will not be a straight line. It is a straight line so long as the mass is constant. In case of rotational motion, it is the same thing. In that case, the force is the torque applied. In that case, the position is the angular position. In that case, the velocity is the angular velocity, angular acceleration, and exactly the same equation holds. Only in that case, we often write it as F is equal to I d omega dt. Omega is the angular velocity, and I is the moment of inertia. By the way, these were vectors, right? So, in this case, is that a vector? If I say it is a vector, then what is the direction? You are rotating it, after all, you are giving it. In that case, it is still a vector, and the vector's direction is by the corkscrew rule. So, that is the direction of the vector. So, f is a vector, omega is a vector, all these are vector by the corkscrew rule. All right. So, that is the definition of the mass or the moment of inertia. Now, let us come to the second type of, this was, remember, this is in general called the inertial element. We will not use the mass element, it is an inertial element, an element that has the property of inertia. Again, the property of inertia is that it tries to maintain its velocity status, it does not want it to change, and if you are applying a force to make it change, then it sort of resists. That is the property of inertia. The second element that we will be considering is the compliant element. The compliant element is essentially the spring. So, these two extremities have certain positions in the unstretched condition, and if you pull it, thereby change the position. Suppose these two position, suppose this is fixed and this is defined by the position variable q, and you are pulling it. What happens? What is the terminal characteristic? I am not concerned about what happens inside the spring. What is the terminal characteristic? What is seen by the terminals? A force is developed that is equal to k times q. Q is the position. So, this q has 0 value when it is unstressed. We have assumed, we have defined the coordinate axis that way, and as the q changes, the force is developed which is proportional to the q, and the proportionality constant is k, that is spring constant. Okay. Earlier mass was the proportionality constant, here the spring constant is the proportionality constant. So, you can say that there will be a similar graph drawn where q is here and f is here, and you would normally get a straight line. If you do get, then only this equation is valid, else not. But in actuality, what happens is that you either have characteristics something like this, slightly off, or you have characteristics something like that, slightly off. Are these visible? Yes. Now, if the characteristic is the black one, then it is a linear spring. What is the characteristic of the blue one? That as you elongate it, the force is somehow going down, right. So, it is softening as you are elongating it further. So, that is a soft spring. On the other hand, this is a hard spring. Even though these possibilities are there, and you have to be alive to the idea that the actual spring in its characteristic may not be exactly linear, but for our purpose we will approximate it by the linear one, which will again be within a certain amount of elongation, not very far from reality. If you stretch it too far, then only all these softness and hardness appears, else you see the difference between the 3 lines up to this point is very small. So, we will go by the linear approximation up to a certain point in this course, and then we will release it, but up to a certain point we will have to go with that linear approximation, because we want to make our life simpler, at least to start with, at least when we are appearing the examinations, we want to do things with simpler equations. So, this is the equation of the, and you can write this also as k, and q is the change in the position. If you want to write it in terms of the velocity, then how do we write it? Integral of velocity dt. So, that is the character of the so velocity and the force are related by this integral relation, remember that. This is a relatively simpler, this will be, you let us see, this will be far more meaningful in our line of analysis. So, f is equal to k integral v dt. So, this slope is in this case k. The third element that we have to deal with is the frictional element. Or resistive element or dissipative element, whatever you call it, frictional element. What is the character? In general, you may have learnt in your school that there are 2 types of frictions, either it is a viscous friction or the static friction. Viscous friction happens when 2 bodies are moving against each other, but there is a film of liquid in between them. There is something with a viscosity in between them, that is the viscous friction. And if 2 dry bodies are sliding against each other, then it is a dry friction or static friction. Their characteristics are entirely different. Let us first deal with the viscous friction. For viscous friction, the force is equal to, or force is proportional to, let me write it this way, force is proportional to the relative velocity between the two bodies. And we will in general represent that proportionality constant as R, because it is a resistive kind of element. We will in general denote it as R. So, this equal to R. So, the relative change in the position, in terms of that if you write, it is dq dt. Now, in case of the Coulomb friction or dry friction, the character is that if you have such kind of a body and if you are applying the force, for some time it does not move, it does not move, the force builds up, but still it does not move till a certain point when it starts to move. Okay. So, there is a critical value of the force below which it does not move, above which it moves. So, if you plot the characteristic, then it will be, say here is the force, no, let me draw the force here and V here. For zero velocity, the force builds up, and till a certain value still it does not move, and then it starts to move. When it starts to move, immediately the force falls and it drops like this, but not much, force is still there, and thereafter as the velocity is increased, it sort of remains more or less constant, but actually it slightly drops, not much. The, if you draw the constant value, it will be something like this, but it slightly drops. It can be approximated by a constant value. That is why in most modelings you will find it is approximated by a constant value. If it is moving in the opposite direction, it is like this. So, it is a very clearly nonlinear behavior. The Coulomb friction is a very clear nonlinear behavior, where as the velocity increases, it is, here is more or less straight line, here is more or less straight line, but in between there is a jump. So, that is the Coulomb friction or dry friction. Static friction, yes. No, that is the characteristic. See, there is a stick slip kind of motion. So long as it sticks, a certain force builds up and then slips. When it slips, then that much of force is not available between the two bodies, and so it just drops. Now, out of these two, again, for our purpose, till a certain point in this course, we will mainly deal with the viscous friction. Why? Because that is the most prevalent type of thing that you encounter in industry, because all the motors, all the elements that you design, we always put some oil, right, lubricant. Why? Because you don't want this. This results in sound, chatter. When when somebody entered, there was a cracking sound in the door. That's because of this static friction. And you put some oil, the sound goes. That becomes a viscous friction. So, we always want to use viscous friction, and since most engineering systems are designed to use viscous friction, for all practical purposes we will use this equation. But later, when we want to model more accurately, we also include what can be done with the Coulomb or dry friction. Now, at this stage let us see the other end of the story, the electrical systems. In the electrical systems, our approach would be, why are we discussing electrical systems? Because when we try to model actual systems, they could be electrical, they could be mechanical, they could be electromechanical, mixture of the both. So, we will also need to understand electrical systems, but the main approach would be, in what way are they similar? You would notice that they are in many ways similar. That is why you may have heard the term electrical equivalent. Most mechanical systems can be made into electrical equivalent. Why? Notice that if you consider, suppose you consider a inductor, and you have got some kind of a voltage source and a switch. What is the character of this inductor as seen between the terminals? It is some kind of a relationship between the voltage and the current. And what is the current? What is the relation? Simple stuff. Now, the current is the rate of change of rate of flow of charge. So, you can write right, and the voltage is EMF, electromotive force. That is why you can easily intuitively say that this voltage is similar to the force in the mechanical system. And if we look at the inertial elements slide, you would notice that the force is equal to mass into acceleration mass into d2q dt2. So, immediately the L appears to be equivalent to the mass, inductance appears to be equivalent to the mass, but that equivalence will be valid if the charge becomes equivalent to displacement position. So, the equivalence would be the charge is equivalent to the position, current is equivalent to the velocity, okay. Rate of change of current is equivalent to the acceleration, inductance is equivalent to the mass, and the voltage is equivalent to the force, electromotive force is equivalent to the force. Then the whole thing is exactly the same, to the extent that if you now close the switch and allow the current to pass through the inductor, and if you see a certain way of rise, if you do the same thing here, its variable will change exactly the same fashion. There is no fundamental difference between the electrical system and the mechanical system, they can be exactly equivalent. Clear? So, that is the character of the, and also there is another intuitive similarity that you have to consider. What is the character of the inertial element? That if you push it, if you apply a force, it sort of resists, it does not want its inertial status to be changed. It was already moving with the velocity v, if you apply a force, you are changing the velocity v, and that is what it resists. Inductor, it resists the change in current, it resists change in current. That is one of the things that you learn in first year electrical engineering, that inductor does not allow its current to be changed instantaneously. Same thing with the mass. Now, let us talk about the next element, that is the compliant element. Compliant element in mechanical was the spring, compliant element in the electrical domain is the capacitance. Here the equation is I is equal to C right, that is the equation that you have learnt, or right. And where is the slide for the compliant element? spring slide here. Force is k times v dt, here is the velocity. Here the force, there is a problem, since the velocity is represented as v in mechanical domain while the voltage is represented as v in the electrical domain, do not mix them up. This is the equivalent of the force. Force is 1 by c times velocity dt, I is the velocity, right. So, you would notice that still the same equivalence holds, equation is exactly the same, only the k of the spring constant is equivalent to 1 by c, not the c. Many students make this mistake, the equivalence is to 1 by c. Okay. Clear? And now let us come to the resistive element. Where that is the electrical resistance property, Ohm's law. Here remember, the Ohm's law is Ohm's law actually defines the term resistance, because that is the proportionality constant between So, if you are asked to measure a resistance, how do you actually do? Most of the students, if I ask this question, how do you measure the resistance, he or she will say that I have the resistance, I apply a voltage battery and I measure the current, that is it. No, that is not it, that is not it. You have to obtain the slope of the curve of this line. So, you have to apply a variable voltage, for each voltage you have to measure the current and thereby you have to draw the line, that will give you the R, not just one value, because there are always measurement errors. If the one value comes here, you will get a completely wrong value of the, but if you have many ones, then you will get a more or less a straight. So, that is the property of the resistive element, but you would notice that the resistive element in general is exactly the same as the viscous friction element in mechanical domain, because here the force is r times the velocity, here the force is r times the velocity. Clear? So, we have established the equivalences of the electrical and mechanical systems. There are two other elements that would require your attention. One is the voltage source. We will in general name it as source of effort. In electrical domain, that is the voltage source. In the mechanical domain, that is the externally applied force. If something is applied on a body, that is the source of effort. Now, what is the character of the source of effort? Let us try to understand this, because most people, I do not know why they do not understand this elementary point. Suppose you have got a voltage source, say a battery, and you have got something here, some kind of a electrical circuit here. What is the character of the voltage source? It gives a definite voltage across this point, but the current that will flow is not dictated by this fellow. Current that will flow is not dictated by this fellow, it is dictated by the rest of the circuit. So, it is a voltage source in the sense that the voltage is an independent variable, but a thing's behavior is composed of two things, both the voltage and the current is not an independent variable, it is dependent on the rest of the system. So, here it is the source of effort in the sense that its effort is an independent variable. Notice the mechanical domain, again something that very few people seem to understand. Suppose there is a mass and there is a fellow who is pushing it like this. He is applying a force, but notice the plight of this poor fellow. if this mass moves, he has to move with it. He has to move with it, and how it will move, that cannot be dictated by this fellow, that will be dictated by that system. So, the velocity, or in electrical domain the current, is not dictated by this fellow, but the force is dictated by this fellow. That is the source of effort.
Sir, but it also depends on man also, that how much force is applied.
Yes, a strong man every day going to the gym obviously will apply a more force, that is okay, but he is dictating how much the force is. He is dictating how much the force is. But the rest of the system is dictating how fast he has to move in order to apply the force, in order to keep applying the force. Like here, the rest of the system, whatever is the circuit, that decides what will be the current flowing through that system, exact equivalence. Then we have to talk about the source of flow. In electrical domain, it is the current source. So, it is drawn like this with a certain amount of current, say 1 ampere flowing. There is some kind of a system here connected that immediately says that the current here is dictated by this fellow, the voltage is not. Voltage here, whatever is whatever appears across this is not dictated by this source element, it is dictated by the rest of the system. And both these variables, the voltage and the current, can be dictated by no element. Nobody can dictate both the things, and that is what the elementary thing about the interaction between elements is. I will come to that in details later, but try to understand that here the current is the independent variable, the current is dictated. The moment you say that, do you understand that this source of flow cannot be open circuited, because if you open circuit, the current goes to 0, then it violates these conditions, it cannot be open circuited. So, it can only be short circuited. If you open it, it goes to the rest of the thing, and then it works. It will be very interesting to know what is the mechanical equivalent of a current source is. Do you know what is the mechanical equivalent of a current source? In every machine it is used, actually, every say car, motorcycle, scooter, everywhere it is used. It is something like this, it is called a cam, where an odd shaped body, and there is a plate, and here is a shaft, and this is the axis on which it rotates. So, depending on the shape of this shaft will go up and down. Okay. So, on this one, it is actually forcing a certain flow. Do you see? It is not giving a force, it is forcing a certain flow, it is a source of flow, it is equivalent to the current source. Can you see that? So, it is equivalent to the current source, it is called a cam. So, depending on the kind of movement that you want here, you give a specific equation to this body, it is a closed loop, you give a specific equation, accordingly as it rotates it goes up and down in that specific manner. So, at that point you have applied a velocity. So, it is equivalent to the current source. So, that more or less completes the things that we have to consider initially in order to build up very, very complicated things. All the things that you see, engineering things that you see around you, are essentially composed of these things. So, let us start. What we will do is, first let us go by the mechanical way, that means let us treat the mechanical systems. And in the mechanical systems, you know the elementary equation is given by Newton, that is force is equal to mass into acceleration, or this being a double derivative of the time, immediately you can see that this is a differential equation. So, simple. For anything, if you can identify the force, you can identify the mass, then you can write down the equation. Saying is easy, but doing is not. We will see slowly that in case of more complicated system, this becomes somewhat difficult actually to do. But let us start with a simple system. Suppose you have a system like this, a mass m, a spring k, and the q variable, the position variable, is measured from the point where the k is unstretched, and suppose you pull it with a force F. Then how to look at it? Newton says that what will happen is that because of this application of the force, the momentum will change. So, rate of change of momentum is what is written here. So, you will write the equation like this. Very close to the time of Newton, D'Alembert, probably you have heard his name, D'Alembert gave a very similar but slightly different way of looking at it. He says that if there is the application of a force that tries to unsettle a mass from its own inertial status. Inertial status means either in state of rest with respect to something or state of uniform rectilinear motion. If you try to disturb it from that, then it sort of resists it. And how does it resist? By applying an equal and opposite force, and that equal and opposite force has a magnitude of this. So, according to Newton, if you draw the what is known as free body diagram, it is like this, F, and here it is. If it is moved by amount q, then the force that the spring applies is kq. So, these two are. In D'Alembert, he says that the free body diagram would be F kq, but at the same time, because of this difference, the positional status will change, and here an opposing force will be applied. So, what we normally do is, if it is a complicated structure, then for each mass point we draw such free body diagrams and simply equate the elements appearing in it, simple. So, in this case you can write down the equation as m q double dot plus k q is equal to F, that is it, simple stuff really. Okay. So, that is the equation. So, you would say that normally the dotted variables are to the left and the undotted variables to the right. So, you will say m q double dot is equal to F minus, that is it. This case it was simple. Why was it simple? Because this fellow mass has only 1 degree of freedom, only 1 degree of freedom. It can only move this way, it cannot move this way, it cannot move this way, that is why it was a very simple equation. But in general, it is not difficult to see that the position of a mass is a 3-dimensional quantity. There will be 3 variables x, y, z. So, in general the position will have to be written as a vector r with 3 numbers in it, right, for one mass. Supposing there is a mass connected with something with another mass, then for both you will have to write such things. If there are 3 masses, if you go on increasing, just imagine the solar system, they are all interacting with each other, then how many? Then depending on the number of mass points, we will lump again the sun into one mass, the earth into one mass point, and then we will say for each mass point I will need 3 coordinates to define it. So, the positional status of each mass point is defined by 3 numbers, 3 real numbers. How many real numbers do you need in order to specify the positional status of such a system? 9. Okay. Now, in mechanics we have a nice way of looking at things. If there are 9 numbers required to specify this, there is no fundamental distinction between the x coordinate of this body and the y coordinate of that body. They are on the same pedestal, same kind of variable. So, there are 9 variables equal importance. What we do is we say that okay, now let us imagine a space in which these coordinates are all these 9. You will not be able to draw a 9 dimensional space, all right, but do not draw, just imagine that there is a space with each of these variables as a coordinate, x coordinate of this one, x coordinate, y coordinate of this one, z coordinate of this one, x, y, z of this x. So, there are 9 coordinates. This space, the advantage of this formulation is that in that case the positional status of this whole system is just one point in that space, and if the position changes the point moves, that is it, clear. So, that formulation, that space is called the configuration space. With q j as coordinates. The q j's are the coordinates. Notice the advantage. This concept came very soon after Newton, that you can represent the whole positional status of a system by means of an imaginary space in which the position of each body there is represented by 3 numbers, and all these bodies taken together, their position coordinates taken together give me a space. It will be a vector of how many dimension? Yes, in this case 9, or in general if there are n bodies, there will be thrice n of these numbers that you rewrite in that vector. It is just one vector. The point is that so far a rather simplistic way would be that if there is a, if this is the actual space, 3 dimensional space, there is a body here, there is a body here, there is a body here, then you would say here is a vector, here is a vector, here is a vector, and so on and so forth. But now in our this representation, that whole thing becomes just one vector. This whole thing becomes just one vector in just one space, but now it will not be a 3 dimensional space, it will be thrice n dimensional space, but nevertheless that many vectors, a single point in that space representing the positional status of that system, clear. So, that is the concept of the configuration space. obviously the configuration space is many dimensional. There is a conceptual advantage in writing it this way, but then it is many dimensional, but in actuality all that many dimensions are not necessary. Why? Because most of the motions are constrained, most of the motions are actually constrained. You cannot have every freedom in motion. For example, if this fellow is here and I am trying to motion, obviously I am trying to move it, obviously it is not free to move in this direction, it is constrained. There is a constraint. If you have a pendulum, what is the constraint? No, in that case pendulum moves like this, it is constrained to move on the surface of a sphere, right. It is constrained to move on the surface of a sphere. This fellow is constrained to move on a plane. If you have a planar pendulum, it is constrained to move on a circle. So, these are constraints. And have you ever ridden on a roller coaster? In the fairs, you are made to move in specific trajectories. Stomach churning thing, but nevertheless, have you felt that is also a constrained motion? You are given specific equations of motion forced on you. So, whenever actually most systems have these kind of constraints, and I will show that is actually advantage. Why? Because if the motion of this bob is constrained to move on the surface of sphere, it reduces the dimensionality of the system. Originally it was 3 dimensional, but now you do not need 3, you need only 2 in order to specify the position on the surface of a sphere. If it is a planar pendulum, you need only 1, just the angle, in order to specify it. So, if you have this one on the sheet of paper on the table, then you need only 2, you do not need 3. So, even though in theory you need thrice n number of coordinates of the configuration space, you do not really need them, and that is advantage. We can simplify the formulation a lot by using that advantage. But notice that each, in order to force it to remain on that constraint, whatever is constraining it has to apply a force on it. For example, right now this paperweight is being applied on, forced by the same force as its gravitational force by the table. There is a force acting upwards, that is what keeping it here. In case of this pendulum and its motion, what is the force? No, the constant force is this. That is what is keeping it constrained. If you do not have this force, it will move away. And in case of the roller coaster, you can feel that constant force, right, in your stomach. You can feel that constant force. The point that I am making is that the body's motions are constrained because the whatever is applying or forcing it to that constrained motion is applying a force on it. That is called a constant force. That is called a constant force. So, we will call it Fc. And if there are j number of bodies with j number of constant forces, it will be this. Clear? So, again to repeat, the motion of most bodies, not all bodies, for example, the motion of earth in the solar system is not constrained. It can move any which way, it moves in a particular way because of the equations of motion. But the motion of most bodies that we have to deal with are constrained, and that gives us a major advantage. That gives us a major advantage, and that advantage we will try to reap. But then the moment you consider the constant force, what becomes the equation of motion, Newtonian equation of motion for each body? Then it becomes m for each body, m times acceleration or equal to the applied force minus the constant force. Okay. You can have this body, you are forcing by something, that is the applied force, and this is the constant force. If this is attached to other bodies by means of springs or whatever, then those things are also the applied forces applied on this body by some other body. So, they will be categorized under the category of F, in general called the given forces, and these are the constant forces. Every body will have this kind of motion. For n number of bodies, then what you will do? You will write this equation. You will immediately see that you are not getting the advantage out of this simplicity, because for each direction you will have to write this, each coordinate you will have to write this. If there are n bodies, there will still be thrice n equations. So, that is one major disadvantage of the Newtonian formalism. Newton gave us a way of writing the equations all right, but soon after, within a span of some 100 years, some additional thing had to come in order to enable people to write the equations in a more elegant manner, and that is what we will study in the next class. Okay. Thank you.